She started out up in Canada, where she got her undergraduate degree in both physics and astronomy with a minor in mathematics at the University of Victoria, which is in BC, Canada. She then received her master's degree at St. Mary's in Nova Scotia before attending Laval University for her PhD. She then completed postdocs at both Caltech and Trent University before teaching at Mount Allison University and both at Yale in the astronomy department, before ending up where she is today with us in California, down at Cal Poly. So today she'll be telling us about some of her work. So take it away, Dr. Edwards. Thank you so much for being here.
Thanks. Yeah, I have a few personal photos. Properties of galaxies on the edge of distant superclusters. So galaxies on the edge, properties of galaxies on the edge of distant superclusters. So what is that? What are we going to talk about in this talk? So why study galaxy clusters and galaxies and clusters? What is a galaxy and what is a cluster? So NASA has several objectives, things that NASA deems really important questions that as a community, as astronomers, we want to answer. There's questions about planetary science. There's questions about stellar evolution, astrobiology. There's questions about galaxy evolution and cosmology. And we have questions about instrumentation, and all of these things NASA thinks are very, very important, and has different tasks or major questions that it asks that us astronomers as a group then go and try and answer. So the Cosmic Origins program at NASA asks, how did we get here? And my work is primarily focused on this question. How did galaxies evolve from very first systems to the types that we observe in the here and now, such as the Milky Way in which we live? So what is a galaxy, right? Galaxy is a collection of stars plus gas and dust, and of course, dark matter, right? Stars, gas, and dust, and dark matter. And there appears to be a huge diversity of galaxies in the universe. So in the background are some images of a bunch of different types of galaxies that we see. But amazingly, you can kind of classify galaxies into two broad buckets using Hubble's galaxy classification scheme, so from like 100 years ago. And we see on the left that galaxies are elliptical, can be elliptical, so they're red. Well, actually, my students usually say this doesn't look very red, it looks orange or brown, but an astronomer would say these galaxies on the left, E0, E3, E6, they're all red systems, elliptical galaxies, red systems. And then on the right, they're sort of blue, at least at the very edge, they're very blue systems. And you can pretty much take most galaxies in the universe and classify them at local universe, classify them as elliptical or spiral. And if you include another bucket, irregular, then you can basically get everything in. But the spiral galaxies have this disc-like structure to them. They've got a bulge, a lot of stars in the middle. They've got these spiral arms. They have these blue colors, which tells us that there are young stars present. They have tons of gas and dust, and they're common in the field. Okay, so not clumped together in dense clusters, for example. On the elliptical side, if you look at the shapes, you'll see there's less sort of detailed structure there, right? They're spherical or elliptical and smooth. The colors are red, as I mentioned before, and there's very little, compared to spirals anyways, gas or dust in these galaxies. And they're common, instead of what we call in the field, they're common in clusters of galaxies. So near, grouped up with, tens, hundreds of other galaxies. So galaxies on the edge, property of galaxies on the edge of different distant superclusters. So our next question might be, what then is a galaxy cluster? A galaxy cluster is a bunch of galaxies plus dark matter and also gas. lots of gas, lots of hot gas. So the picture on the right here is from an X-ray observing telescope. So you're seeing gas that's emitting at like a million degrees here. And the amount of, hydrogen gas that's causing this emission is, if you added up the mass, is a lot more than all the stars of all the galaxies within the cluster. So if I show you an optical image, a picture that your eyes see of a galaxy cluster, the core of a galaxy cluster here, each one of these fuzzballs that you see is a galaxy. And so this galaxy has all those stars and gas and dark matter themselves. But then, imagine, and I'll show you a picture in a second, but imagine permeating through all of these galaxies is this hot X-ray emitting gas, right? That if you add up all those atoms, represents a huge amount of the gravitating material of that system. Okay, so we have the galaxies here that we see with our eyes, and I can overlay on purple the image from that X-ray observing telescope to show you where all of the hot gas in the cluster is, right? So it permeates through all those. And then, of course, that's the stars we're seeing the representation of the X-ray gas as well. And the galaxy cluster, just like the individual galaxy, has lots and lots and lots of dark matter as well. And so I guess I asked this, asked my class, what's a galaxy cluster? And recently a student had answered, oh, it's a cluster of galaxies. And I gave her a sticker because technically that's right. But when you think about a galaxy or a galaxy cluster, make sure you're thinking about all of the stuff you can't see with your eyes, right? This hot gas and the dark matter as well. Okay, so we have galaxies, we have galaxy clusters, and we're going to be thinking about galaxies in this talk as they move through galaxy clusters. So we're going to be thinking about these galaxies that house their own gas inside of them, pushing through this, we call it intercluster medium for fancy, but pushing through the gas in the galaxy cluster. And we're going to ask later on in the talk what might happen to those galaxies. So that we have a good visual of what's going on, we can look at this movie that I did not make, this famous movie of the illustrious simulation. So this isn't a cartoon that you're looking at. You're looking at computer simulation. So that means that we put all the equations of how gas interacts with itself and the surroundings, and we put in the equations that describe how mass, the galaxies, right, and the dark matter in the galaxies, how that moves together under gravity. We put all of that in the computer and we let it run to see what happens. So on the left are the galaxies in a galaxy cluster that's building, and kind of as you would see them with your eyes. So you can see there's a lot of, there are a lot of messy systems here, some irregular systems. And as we watch, we're going to see that they settle into old elliptical systems. And on the right, you're seeing the exact same piece of space through the same period of time in the simulation. But instead of watching the galaxies as you would see them with your eyes, you're watching the gas inside the galaxies and what happens as the galaxies sort of tumble towards each other, tumble towards each other, and their gas is getting, ripped out of them, and these supernova explosions are going off, or these big explosions are going off as time goes by. So you'll see now, as we've gone from earlier in the universe down to today, we've built this big red elliptical galaxy. And whereas 100 years ago, Hubble's tuning fork, the idea was sort of that, maybe galaxies start as elliptical and then become spiral. At Hubble tuning fork we saw earlier was thought to maybe be an evolutionary tract. Today, it's sort of flipped around, and we think that galaxies start as blue spiral systems, and then as time goes by, they merge and interact with each other, and that gas gets used up or blown out, and eventually they settle down into these elliptical systems. Okay. So this is a map then taken from a similar computer simulation to the one that we just looked at, but now what you're looking at is these orange points are the dark matter. It's not the gas, it's not the stars, but it's the dark matter in these systems. And the zoom in here is about the same scale, about the same size, several galaxies across as the simulation, the video we just saw, but it's embedded into the much larger chunk of the universe. And when we do this, we see the large scale structure of the universe come out. So before I was talking about finding galaxies in the field or in dense clusters. And this is what I mean. The universe, if you Google zoom out enough, it's not galaxies smoothly distributed everywhere in the universe. No, there are regions where the galaxies, in this case, they're dark matter hearts, right? But the stars follow that. So there are galaxies that clump together to form these dense cores. So this is like, tens or hundreds of galaxies that make a cluster. And then there's these areas here that are totally devoid of any matter whatsoever, which we call voids. And then there's these beautiful chains of matter that seem to link the clusters together. So those are called filaments. So we can think about the large scale structure of the universe, for the purpose of this talk anyways, is we can think about dense galaxy cores and filaments that extend from those dense galaxy cores, and then regions devoid of matter, sort of in between those filaments, voids. Okay, so here's an example. This is a cartoon based on real data of a chunk again of what we were just talking about, a chunk of the universe showing one galaxy cluster, and the core, dense core would be down in here, and with just one filament extending off of it. And this is some work that I did with my colleagues when I was at the NASA IPAC housed at Caltech about a decade ago. And we were looking at these filament areas and we were wondering, does a galaxy care what its environment is? Is a galaxy going to be behaving differently if it's in a cluster core versus if it's in a filament? And in this cartoon, the red, again, based on real data, the red points are galaxies that we identified as old and red colored. And the blue dots are galaxies that we identified as forming a lot of stars. So they definitely have a young component. And we were able to see that there are a much higher fraction of blue to red, young to old, star forming to dead galaxies in the filament than there are in the cluster core, right? In the cluster core, you can see this with their eyes. There are more red than blue dots, and on the edge, there are more blue than red dots. So this is something that I've been thinking about for a while, is how galaxies evolve, how they change, depending on where they are in the universe, if they're, they act differently depending on a location, and is sort of the initial thrust of the rest of the talk, of the science question we'll ask in the rest of the talk. But before we get to that, so I've showed you a simulation, which is, all of the equations that we know that describe physics as we know it in the computer running, giving us a view of that. And then we have this picture, which is certainly a cartoon, but each dot really represents the location of an actual galaxy that we've observed. And the colors represent, properties of the galaxies that we've determined through observations. But now I'm also going to show you an actual cartoon, okay? So I've been very excited to work with student Angela Chawla for the last year or two, who's actually an art and design major. And it's been really fun working together because she has been making actual cartoons based on some of the ideas that we're trying to explore. So here she's got, see if you can figure out what these blue wavy wiggles are in your head before I explain it. But what she's cartooned up is, here's a galaxy on the bottom right here. And you can see it's got a little bit of star formation going on. There's certainly some gas in there. And it's about to head in to the denser cluster region over here. And you can see that she's put lots of galaxies in this cluster, and this blue stuff is that hot X-ray emitting gas. And she built us, oopsies, oh no. She built us a nice little animation of the galaxy going in and losing its gas and turning old as it goes into the galaxy cluster core. So keep that cartoon in mind as we dive deep, take a deep dive into the actual astrophysical data. So our question is there evidence that any particular environment drives the changes seen in galaxies? The changes I'm talking about being going from some sort of dust-filled, bursty, star-forming young galaxy into an old, large, red and dead galaxy. Okay, is there any evidence that suggests that a particular environment changes these galaxies? We might also ask questions like, how does this happen, or when does this happen? But in this talk, we're asking about where. And one specific question we can ask to sort of support that would be, what is the frequency and star formation rate? So how often and how much, how many stars, how often and how much star formation is there for galaxies throughout superclusters? Supercluster meaning the cluster core, the outskirts of the cluster, and the filaments that maybe come out of that cluster. Okay, that's what I mean by supercluster. So what is the frequency and star formation rate for galaxies throughout a supercluster in all these different environments? Okay, so the figures that I'm going to show are based on this recent paper. I should have updated the cartoon here. It was published earlier this year in 2021. And the name of the paper is Efficient Detection of Emission Line Galaxies in these two telephone number superclusters using CTEL. So I'm sure most of those words don't mean anything because they're, acronyms and jargon at the moment. But by the end of the talk, hopefully you can read the title and it will make good sense. What I want to highlight here in this image is that these two undergraduate students here at Cal Poly, Kevin Zhang and Jackie Fraga, helped quite a bit with this paper. And in fact, Kevin's plots are in the article, so he got authorship here as well. And this work is done with some colleagues of mine in Europe. So CTEL is an imaging spectrograph. So that means it will take an image of a piece of sky, and for every single pixel in that image, you'll get back a spectrum. Okay. And this is very powerful because you can use the pieces of this spectrum to determine all sorts of things about the galaxy's star formation history and motions as well, internal motions of the stars. So CTEL is an instrument then on the Canada, France, Hawaii telescope, which is pictured down here. This is a 4.5 meter or 4 meter mirror telescope that is on Mauna Kea in Hawaii. And what we're eventually going to do is isolate these particular emission lines, 023726. So some oxygen lines, are going to isolate these emission lines and study the characteristics of these emission lines inside the galaxies in this cluster. Okay, and we're able to do this pixel by pixel with this instrument, which is super exciting. So here's another one of Angela's cartoons. This is a cartoon based on real data. And what she's showing here in this picture is one of our superclusters. We looked at two. And she's showing you the punchline. So I'll tell you the punchline right now, which is that we find a lot more galaxies that are young, that are forming stars in the filament, okay, that extends off of this cluster core than we find in the cluster core. In fact, we don't find any in the cluster core, which is not unusual. Okay. So that was Angela's beautiful cartoon. And here's my publication ready cartoon. So the purple is showing you the galaxy density It's a density map. So where the lines are close together, it's saying there's lots of galaxies here. So this is the cluster core. And where the lines are far away from each other, there are fewer galaxies per, area. So this is the filament out here. And the individual dots and stars are the locations of single galaxies that have lots of star formation right now. They're blue and they're forming stars right now. The red is locations of some other galaxies that aren't actually forming any stars. And one thing that we can do is count the star forming galaxies in the different regions of the cluster. So what we find is that 90% of the young galaxies, of the star-forming galaxies, these disk galaxies, the spirals, are found in the filaments, almost all of them. Some of them are found on the edge of this subcluster as well. Now, how do we do this? How do we determine the star formation rate? Okay. What we do, as I alluded to before, is we have spectra. So here's my spectrum, or here's several spectra of galaxies in the supercluster. I have these spectra, and I'm going to use properties of the emission lines in order to determine which galaxies are star forming and what the star formation rate is. So if there's no emission line, then we say this galaxy is not forming any stars. If there isn't an emission line, then the galaxy, we assume, this is an assumption for the astrophysicists out there, that the emission is coming from stars, from star formation. And so what we do is we calculate how many stars are forming, how many solar masses per year. So how many stars, the mass of our sun roughly per year, are forming in this particular galaxy. And we do this using this relationship that the observable, what we measure is the luminosity. Okay, so the luminosity of this line, how intense, how bright this line is here. Okay, and then so for us, for astronomy, the flux, good physics concept, the flux is the amount of energy crossing a unit area in a unit time. And the luminosity is related to the amount of flux that you have a certain distance away or from your source. Okay, so in order to compute this property, we need to know how far away the galaxy is from us. And that's great. We have a way to do that. We use what's called Hubble's law. So any people who have taken astronomy, this is going to sound familiar. And if you haven't taken astronomy, I think I can take you through the logic quite quickly. So to get R and D mean the same thing here, how far away our galaxy is. And we can figure out how far away the galaxy is by this relationship that we have noticed, that Hubble noticed, between how far away, how fast a galaxy is moving away from us, and how far away the galaxy is, and the relationship between those two things is called the Hubble constant, H naught. So put that on hold, and I'll show you a plot of that in a second. But using this equation, we also need this other value, V, the velocity, how far away the galaxy is, how fast the galaxy is moving away from us. So for those of you who have taken astronomy or who are astronomers, this is the redshift. Redshift is the velocity divided by the speed of light. And for those of you who are physicists or just dropping in, we get the value of that speed. We can get it from our measurements. What we look at is how far away from our expected wavelength the emission line we're looking at actually is, and that will give us back the speed that the galaxy is traveling. And so this V, H equals V over D relationship is this famous relationship from Hubble from, again, 100 years ago, which shows when he looked at these galaxies, and others looked at these galaxies, he just noticed that the distance away from us that the galaxy was related to this recessional speed that was measured. And the slope of this line is so special, we give it a name, H naught. And we use a value, 70 kilometers per second per megaparsec, in doing these equations. So it's great. So by measuring essentially how much light is under our emission line and how shifted from the expected location our emission line is, we can actually derive the luminosity of O2, oxygen, and from that, derive the star formation rate. So those are the details of how we do that measurement. Okay, a second measurement that I will look at, the second thing that we look at in this study is that we notice is that many of these star-forming galaxies in the supercluster have signatures of going through mergers, of merging right now. So that means that either their shapes are kind of look messed up, like they've just passed near another galaxy and gravitationally interacted with the stars in that other system, or that they just have galaxies that are curiously very close to each other. Now, these can, of course, be optical illusion, right? That galaxy that looks like it's close might not actually be very close in the forward or backwards direction from you. But we notice a fair number of them. So statistically speaking, some of them probably are real quote unquote close pairs. Okay, so we notice that the star-forming galaxies are in the filament and that many of them are merging. And I took you through the details of exactly how we know whether or not a galaxy is forming stars. And I'll take you through the details of how we know whether we think a galaxy is merging, and those will be the only two physics details that I'll talk about, and we'll go back to the big picture after that. But let me take you through a little bit of physics on how we determine if a galaxy is merging from the morphology, from the shape of the galaxy. And we use this Gini M20 set of statistics. So we'll be going through the details of this. But what I do is I plot all the galaxies on this Gini M20 plot, okay? So y-axis is this Gini coefficient, and M20 is the name of this fancy statistic, and we'll go to each one. But what you notice here is that there are these lines that discriminate between different types of galaxies. Galaxies that are elliptical in shape will fall in one part of that plot, spiral will fall in another plot, and galaxies that look like maybe they have recently undergone a merger, their shapes are messed up, go in another place on that plot. So the Gini is a statistic that tells you how the flux is in a galaxy, the brightness, the light in a galaxy is distributed. And it's kind of cool because we've borrowed this idea from economics, okay? So a Gini of 0, all right, means that all of the flux is equitably distributed throughout the galaxy. Okay, every pixel that makes up that galaxy has the same amount of light, has the same brightness, has the same flux. Whereas Gini of 1 means that the distribution of light in that galaxy is totally inequitable. One pixel has all the light and everything else is essentially black in that galaxy, okay? So more uneven distribution of flux is towards a 1 in that case. M20 is a statistic regarding how far the bright pixels are from the center of the galaxy, okay? So technically, it is the normalized second order moment of the brightest 20% of the galaxy's flux. And I think the reason I really wanted to get this equation on you on here is for, I think most of you will have taken first year physics. And so you can kind of think about the center of mass, okay? The idea of tracing sort of the center of mass, the center of light, okay? Because you've studied this idea of moment previously when you study a center of mass. So the total, what I'm writing down here, M total, the total second order moment is the flux in each pixel multiplied by the squared distance to the center of the galaxy. So that's the part that should sound familiar from mechanics. Summed over all the galaxy pixels. Okay. So how far away are the bright pixels in the galaxy from the center? Is most of the bright light in the middle of the galaxy, or is it in some clump way on the edge of the galaxy? Okay. So the way that I do this, and I was hoping that this would look familiar to some of the students as well, is using Python, Jupyter notebooks, and there is a package out there called StatMorph, which will calculate all of these statistics for you. So you put in your image and it'll segment it. So it'll find the galaxy pixels for you, and then it'll measure these different statistics, Gini, M20 for you, so you can put them on your plot. And you'll notice for this galaxy cluster that I'm plotting here, about half of the galaxies that are emitting these oxygen 2 lines are merging systems according to this statistic. Okay, so what did we find? We found that moderate density environments host different galaxies than dense cluster cores. So moderate density environment being the filament. So 90% of star-forming galaxies are outside the main cluster, and about 40% of them have merging morphologies. So that's putting the data from both our clusters together. This is consistent with galaxy type changes happening outside the main cluster before the galaxy reaches the core. So galaxies on the edge. Properties of galaxies on the edge of distant superclusters. I'm hoping the title makes good sense to you now. Many of these galaxies are actively forming stars. Many of them are blue. Many of them have irregular morphologies and nearby neighbors. Our data is consistent with the picture that galaxies evolve from blue to red before entering the cluster core. So I do see they have some time left, and I would like to talk about DEI plus astrophysics projects for the remainder of the time. And I'm hoping that you could turn off the recording actually, because there's some unpublished stuff in the rest of this talk. So now would be the other time to please turn off the recording. Thank you. And then I'd be happy to discuss both of these projects at the end.